This video is entitled Building Successful Systems and goes along with Chapter 10 of our Introduction to Information Systems. I'm Dr. Jim Renault from Shawnee State University, and I'll be taking you through this video presentation. This video presentation really is going to focus on systems development and the life cycles of how we do it. The diagram that I have shown here on this slide is not like the diagram found in our textbook or really any other textbook I've ever seen, but it's the way I understand the systems development life cycle and the 5 phases of the systems life cycle. The 5 phases are planning, analysis, design, implementation, and maintenance. You may see some authors leave maintenance out, but I think that's incorrect. And you'll see a lot of authors list that as a sequence of do one, then the other, then the other, then the other, 5 in a row, or 5 kind of in a waterfall where you do planning, you'll fall down into analysis, you fall down into design, you fall down into implementation. And this is sometimes also known as the waterfall method. I like showing them in a circle because of the cyclical nature of life, how things go around and around and around. And really, when it's drawn in a circle, I see this as the never ending wheel of money. Um, as a business person, you're always going to be spending money on projects and life cycles of systems. As a consultant, as a programmer, you'll always have a job because of the never ending cycle of the wheel of projects. So the 5 phases: planning, analysis, design, implementation, and maintenance. And I'll have a slide on each of those coming up. So in the first phase, planning, we have to identify the problem. Does the problem align with our strategic goals? How do we measure success of solving the problem? Do we listen, or should we, or we should listen to stakeholders? And a stakeholder is anyone with a vested interest in a project or a system. So that could be users, managers, people paying for it. Everybody is a stakeholder. Do you create a task force of a group of people that get together to, here, you all have been given the task to solve this problem? Is it internal to the business? Is it a task force of external experts that you're going to bring in to solve the problem? I don't know. And as you're identifying the problem, you have to identify the feasibility of the problem, of solution. Is it technical? Can we do it? Is it operationally feasible? Is it going to fit into the way we do business? Is the scheduling feasible? Can we get it done in a time that fits in our needs? Because if it's a 5-year project, but we're going to be bankrupt before we get it done, well, then that's not going to work. Is it legal? Is it regulatory correct, proper? Is it environmentally proper? Is it ethnically proper, or ethically proper? And then lastly, we need to ask ourselves, and this is what usually people start with first, like my list has it first, the economic feasibility. The money that we're going to invest in a system, in a project, should make us money by the time we're done. There should be a return on our investment, or ROI. We should be able to measure or guess the internal rate of return of how much money we're investing versus how much we expect to come back. We always need to take into account the present value of money. Money spent today is worth more than the same amount spent in 5 years. So we have to do all this economic justification and feasibility to decide whether we should do the solution or whether we should create the system. There are 3 or 4 other videos attached to this week's assignment that go into a quick review of how to calculate internal rate of return, return on investment, net cash flow, present value, and some of those other kind of calculations that we business people and IS people use to calculate economic feasibility. So we've identified there's a problem. We figured out that it's feasible to maybe solve the problem. We've kind of made some economic justifications as to why we should, cultural justifications and others. Now we need to actually gather the requirements. We now need to understand what the problem really is. Um, we need to understand our old systems. We need to understand our systems and processes. We also need to understand that a lot of the time, when we identify a problem, it's really just a symptom of another problem. Oh, well, we're having a problem with our inventory. We can't keep enough in stock. That's a problem. Is that a symptom of a problem with your purchasing system? Is that a symptom of your logistics problems? Is that a symptom of, so you can see it can be a symptom of a lot of different problems. So we need to really figure out what the real problem is. And is it a problem with a system? Or is it a problem with one of our internal processes? We need to understand what is. We need to understand the current system. We need to understand the current processes. We need to understand the reports that people are really using, or the parts of the existing system that are really used, because we can't write a new system. We can't go buy a new system. We can't go replace a system if we don't understand how we actually do business. And often management doesn't understand the details, the nitty gritty of what the stakeholders, the end users, know. So a lot of time needs to be spent in analysis looking at what is right now the current system. We should create a model of our current systems. And we need to identify what's used in that current system. What do we keep? What do we fix? What do we modify? What do we add? How do we make it work? So this analysis phase is often skipped. Oh, well, we know what we need. Management knows what we need. I know what my users need. Don't worry about it. I got it. Maybe you don't. And once you go through this process, often you'll find that you don't understand what the real problem is and how the current system is working to get around it. One of the modeling tools that you'll see used by a lot of systems analysts who are analyzing an existing system or even a new system is something called the data flow diagram. This course isn't really the place to go into the details of a data flow diagram. That comes later in the systems analysis and design course. But I want to kind of show what a context diagram looks like. And a context diagram has three things that make up a context diagram. The first is the new system or the existing system, and you see it in the box there in the middle with the number 0, the system. You see rectangles around the system, and those are other systems that interact with the system we're analyzing. There are also individuals or groups of individuals or departments, or even customers or groups of customers or vendors or other entities. And that's why I call them entities. And what we try to analyze here with this document and with detailed data flow diagrams isn't how the system works, but how data flows through the system. So for instance, you as a customer approach a website. That's a system, right? What data do you give the system? Well, you give it your name, your email address, your credit card information, the items you want to buy, the quantities, right? And that system gives you catalog information, list of items, gives you pictures. It lets you do searches. Oh, that's data leaving you, the search criteria of what you're looking for. And then the result of that search comes back. So by analyzing the data flows between entities, we can kind of then figure out what the system needs to do and needs to store and how it needs to be stored. Again, this is called a context diagram. and is a data flow diagram that you'll see in subsequent classes. So moving right along into the third stage of the systems development life cycle, the design phase. Well, we've done our feasibility, we've done our planning, we know it's going to work, or we think it's going to work. We've done our analysis, we understand the existing solution, we understand what we have today, we understand what the users are using, what they're needing, and we understand kind of where we're going. We understand the data, we've got how data needs to flow, we understand our process. Now it's time to design a system that works. Or it's time to pick a good solution. This is where we actually design the databases, the data storage. We design the reports, the forms, the screens, the systems. We design the procedures. We design the hardware, software, networks. We design all kinds of things. And we also identify some of the other things that we need to identify, like how available is this system? What is the speed of the system? And other kind of non-functional bits of things that we design into our system. Design often starts as a conceptual design and then gets more detailed as we dig into the design. We start with, oh, I want a website. Okay, that's a conceptual design. And we can maybe sketch out with our marketing people some rough ideas of kind of how the website's going to look. Doesn't really tell us much, but it tells us a lot. Then we can get into the logical design of how that website is going to work logically. What pages, how the links are going to work, and all of that. And then we have to design how the actual programs underneath the website works, getting into more and more and more detail as we drive down through this design process. One of the ways that we do design is by a process known as prototyping. Prototyping is to build a model, to kind of build an idea of what we need. There are three kinds of prototyping. There's the low fidelity prototyping, which means that it doesn't work. It doesn't really do a whole lot. It just kind of looks pretty. Low fidelity prototyping can be just scribbling on a whiteboard a layout of a screen, or going into Excel and laying out what you want your report to look like. It doesn't really work, but it gives us a really good idea of what we want and what we need. A high fidelity prototype is a prototype that a user can actually click and use and navigate and move back and forth through. One problem with high fidelity prototypes is users often forget that they're looking at a design model and they're not looking at a real product. They'll often get confused between a high fidelity prototype and because it's not going to be real. It might not even be written in the real language you're going to use to finally develop the system. It's just kind of, it sort of works, but it's a way to play what if games. It's a way to help users see what works and what's missing. It's another way to help gather any of those little missing requirements. Oh, well, what about this? Where is this? I don't know. We left that out. Oops, okay. So you know to add that. And the third type of prototyping is known as throwaway prototyping. Throwaway prototyping is extremely expensive, but throwaway prototyping is used when we don't know whether it's going to work or not. We don't know technically whether we can pull this off. NASA uses a process of throwaway prototyping, or used a series of throwaway prototypes to send men to the moon. The Apollo program was a whole series of launches, and the first Apollo rocket literally just lifted off of the off of the pad at Cape Canaveral and splashed right down into the ocean. Then they shot one up into the upper atmosphere and brought it back down again. Then they took one up, firing multiple stages until they got it into orbit, and then they brought it back down again. And then they put a dog on one and shot it up and brought it back down again to prove that it didn't kill people. Um, and this process of throwaway prototyping is one way that we can build systems. Again, it's expensive to do it that way, but when you don't know what you're doing and you don't necessarily really know technologically whether it's going to work, it might be a way to do things. Remember that prototypes are used to increase a system's chance of success by actually creating a model, something that someone can walk through or can touch or can see or can play with. It really can increase our chance of success. Prototyping can be expensive, but it can be really, 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 really positive and very useful in the design phase. So to move into stage 4 of the systems development life cycle, implementation. That's when we actually do it. It's when we buy stuff, hardware, software. It's when we hire staff, programmers, and analysts and designers have already been hired previously. It's where we actually figure out physically how things are going to work. We do our programs, we do our testing, we do our documentation. We make sure it's secure. There are several ways that we can implement a system, and one of them is known as the parallel implementation. We have our old system, we have our new system, we run them side by side for a period of a week, a month, several months, running them side by side, but that means that everybody is doing double work. But by the time we finally make that cutoff, when we finally turn the old system off and rely on the new system, we're pretty confident it's going to work because we've been doing it in parallel side by side. But that again, sometimes creates a lot of double work. There's the phase in and out, where we use the old system and then we replace part of the old system with the new system. So we're using mostly old and a little new, and then we switch another part of the old system to new. So we're using a little bit more new and a little bit less old, and we phase the old system out and the new system in. There's the plunge. And the plunge literally is one day you say, old system is gone, new system is live. There we go. Well, if a proper analysis and design hadn't been done, then you're going to have users not knowing how to use the system. You're going to have reports and important pieces that users relied upon that may or may not be there. Plunge can be really scary for users, can be really scary for an organization. And what happens if that new system doesn't live up to what it's been promised to be? The plunge can be scary. And then lastly, the fourth way to implement a system is to pilot the system. And a pilot would be, well, we've got this old system. We've got this office over here in I don't know, the Columbus office. Let's let the Columbus office use the new software. Let's switch them over, see how it goes. And after the Columbus office uses the new software for a while, worked out okay? Okay, then now let's move the Dayton office over to the software. And then after the Dayton office goes through it, they found a problem or two, they found an issue or not. And then you say, Columbus is working on it okay, Dayton is working on it okay, it must be ready to go. And then you take the plunge by piloting it with subsidiaries or smaller groups. Again, it's a very successful way to do it, and it doesn't create a lot of double and triple work. It just means that it starts with a series of small plunges before the big plunge happens. So parallel, phase in, plunge, and pilot are kind of the way that we will implement, or it's ways that often systems are implemented. So we talked about ways that systems are implemented, but what kinds of systems are implemented? And I kind of like to think of systems as falling into three big categories. Um, a self implementation is where an organization within a business goes out and buys some commercial off the shelf or something, um, and doesn't really have IT support and kind of locks the data into their own thing. For instance, lots of organizations or lots of subsidiaries within an organization or offices within an organization will create this Excel spreadsheet or this access database that does this really crazy thing that the big system, won't do. And we just kind of go build our own, a self implementation. One problem with that is there's no support. And the data in that self built system is kind of siloed away from the rest of the organization that may need or want that data. And the data is kind of locked into that kind of self implemented solution. Those really aren't the best. Um, there's the idea of insourcing an implementation. Our IT people, our project, and we assume all of the risk of doing it in house, of having our own programmers or our own analysts designing and creating and implementing a system. And then, last, there's the idea of outsourcing it, hiring a consulting firm or vendors or consultants that are experts at it. It gives us a lot less control, and it potentially lets some of our strategic initiative and our strategic information can potentially leak, but it's often quicker and sometimes less expensive. So when we're implementing a system, is this a self implemented system? Is this a system that we're insourcing using our IS professionals, our IT professionals to build, or is this a system that we're bringing in from outside? Implementation can happen in those ways and in combinations of those ways. The fifth part of the systems development lifecycle that some authors don't even list as part of the SDLC is maintenance. People often forget about the cost of maintaining and running a system. They can see the expense of buying it, they can see the expense of programming it, they can see the upfront cost of the servers and all of the networks and all of the security systems, but this system is going to live, if you're doing a big one, for periods of years and maybe even decades. It's going to need to be modified and enhanced for strategic, legal, growth, and all kinds of other reasons that you're going to be modifying and twisting and working with this system. And in a lot of respects, maintenance is, and in a lot of systems, maintenance is often more expensive than the original purchase price of the system, the original development cost of the system, the cost of keeping it alive and maintaining it. It's really an important part of your project, your analysis, your design, your implementation, all have to be focused on the idea that this system isn't a one and done thing. The system isn't a get her done, get it installed, walk away from it. How are we going to care and feed for this system for the long term? Also, as we're maintaining a system, it'll often spawn new systems. We'll be in a system and go, it'd be great if this system did this. Well, is that maintenance to an existing system, or is that really a new system that needs to be created? Those are questions that need to be asked. That's why I draw the systems development lifecycle in a wheel. That's why I draw it in a circle where maintenance spawns back up to planning for new systems. And maintenance may, at some point, you just decide we can't afford to maintain this system anymore. It's too old. It's too decrepit. It's been worked on by too many people. It's too buggy. It doesn't do what we need it to do. It doesn't meet the new legal requirements or the ethical or moral or environmental requirements that we have. It doesn't do the security that we need. Well, we may need to scrap it, but it's from maintenance that we go back into the planning for a new system. Now, the systems development life cycle that we've talked about in all of these slides so far is what's called the classical model of creating a system. There are other ways. There are, quote, modern, non-classical ways. Three of them that I just want to go into are the rapid application development, where instead of the planning, analysis, design, implementation all being in a circle, you plan and analyze, and then you design and implement a little bit of the system. You feed it to the users, and through the users' feedback, you design and implement additional parts. It allows for us to get a system that sort of works out quick and then grow into it. Now, again, that can be really painful if we're replacing an existing system that works with that, because the new system is going to be woefully incomplete. But if it's a brand new thing that we've never done before, that's one way that we can rapidly get a start and then learn what we need as we're moving along. Extreme programming is another non-SDLC way where programmers are often paired in groups or paired in pairs, and the system is built like Lego. We take a piece, we add it to it, we push that out, we get the users happy with it, we build another piece, we push it out, we get the users happy with it. It's kind of like rapid application development, but instead of getting feedback from the users, we know what we need to do. We've got a piece, we do it, we got another piece, we push it out, we got another piece, we push it out. And then there are agile methodologies known as Scrum and some of the others that are about time-based. Extreme programming is based on functions. We're going to write this function, we're going to push it out. We're going to write this function, we're going to push it out. Some functions may go out in a week, some functions may take a month or a longer period to develop. With an agile like Scrum methodology, we say every week we're going to push out a new version of the software. This week we're going to push out a version. In a week we're going to push out a version with fixes and enhancements. And another week, every week we're going to push out, or every 3 days or every month we're going to push out a new version of the program with new features and all of the things fixed. It allows us to develop a system that's always growing, but it's a time-based system. Stop and think about your use of a computer software package. Think about your use of Microsoft Word, for instance. What percent of the features in Word do you use? 80% of the time. To do 80% of your documents, you might use font, you might use a ruler, you might use paragraph, you might use spell check. For a simple document, do you do much more than that? No. Of all of the options and all the menu choices and all the ribbons, you're going to do 80% of your work with 20% of the features of that program. And in an agile development, we get the 20% system and push it out, knowing it's going to take care of 80% of the problems, give or take. Might be 70-30, but we're going to push out the system, knowing it's going to do most of what people need it to do, and we're going to let it grow. We're going to continue to push out new releases on a very regular basis to make it into a 100% system or a 98% system. And we always try to get closer and closer to the perfect system. This completes our video on building systems. I would like to say thank you for watching or suffering through another one. If you liked this video, if you found something important in it or found something good in it, check like or subscribe. I'd really appreciate it. You can contact me at jrenault@shawnee.edu if you have any questions. Remember, this presentation is entirely copyright 2022 by me, James M. Renault, PhD. All rights are reserved under copyright. And again, thank you for watching.